Today we are going to look at uniform circular motion in more depth. We will first start with this idea of centripetal acceleration. Basically we are looking at what is the acceleration of an object that is going around in uniform circular motion. We are going to limit ourselves to uniform circular motion. What is the meaning of uniform circular motion? Omega must be constant, and that means r omega is also constant, so the speed of this particle is constant. So this particle has a velocity like this. As the particle moves around, the velocity changes because direction changes, but the speed remains constant. So when it was here, let me call this point A, the radius vector points like this and the velocity vector is perpendicular to the radius vector like that, and the velocity you know is r omega. When this thing turns around and goes there, the velocity becomes like this. So when I have r vector pointing here, let me call this point B, the velocity is going to look like that, and V is again r omega. Magnitude is r omega, it is pointing like this. So this point, I'm going to call it B. And when you turn around a bit more and you come to this place, the radius vector points like this and the velocity vector points down. Okay, this is also r omega. And when you come to this place, the radius vector points like that and the velocity vector points like this. At each point, let me call this C and this called D. Each point, the velocity vector is always perpendicular to the radius vector. So as the radius turns, the velocity vector is also turning. Okay. First question. If the radius vector takes some time to travel around, how much time would it take? We call this the time period, right? So the radius vector starts here, goes around, makes one nice full trip and comes back. How much time? Time period, you know it is 2 pi by omega. Okay. How much time would the velocity vector take to make this turn? Let's think about that. When the velocity vector was like this, afterwards it's like that, it looks like it is like that at that location. But suppose I brought this velocity here, I can draw a new kind of diagram. So here is my initial velocity vector. Okay. The next velocity vector, I am now going to bring this and place it here. So the new velocity vector is going to look like this. This should have been at A. Whereas this velocity vector would be at B. It is the same speed. I am just calling this point B. And then when the velocity vector becomes like this, the velocity vector is pointing downwards. I am just moving this velocity vector to this place. I am just moving everything to the same location. So this is C, and then when it turns around like this, this is D. You can see that the velocity vector is also going around like this, is turning. Can you see that? The velocity vector is making a turn like this. The radius vector is making a turn like this. The velocity vector is making a turn like this. Okay. How much time does the radius vector take to go around and come back? 2 pi by omega. How much time? So when the radius vector is like this, where is the velocity vector? Like that. This is the actual circular motion. Physically, the object is going around in that circle. This is not actual circular motion. I am just taking all the velocities and putting them at one location. So we call this the velocity space. Like imagine a new space where you take velocity vectors and put them there. Then in that space, the velocity vectors are going to go around like this. Okay. So the velocity vector starts like this, and then becomes this, then becomes this, then becomes this, and it's going around, right? How much time does the velocity vector take to make one full turn? Same time, 2 pi by omega. Why? Because when the radius vector goes here, the velocity vector goes there. Can you see? The radius vector has turned by 90 degrees. But the velocity vector has also turned by 90 degrees. Think about that. The velocity vector, when it goes there, the velocity vector has turned by 90 degrees. It's in a different location. But you know that this vector and that vector, if I just move it, it doesn't make any difference. So this vector, as long as I brought it here, you'll see that it is actually a 90-degree turn. So the velocity vector turns the same amount as the radius vector. So r vector and v vector turn by the same angle in the same time. This is very, very important. In same time. I want us to understand this bit more carefully because it's a very, very fundamental idea. Let us see. So suppose this was the radius vector and this is the velocity vector. If I made this turn, you can see the radius vector turned by 90, velocity vector also turned by the same angle, 90 degrees. Suppose it did not turn, how would it have looked? It would have been like this, it would have been like this, and then the velocity vector will point like that. Can you see that now it has to make a 90-degree turn to come back and become perpendicular? You can see this also when I do a little bit. I don't do, let us say 90 degrees, but suppose I say radius vector turns by theta, right? The velocity vector also has to turn by theta. You can see that here. So radius vector turns by theta and the velocity vector does not turn. It will look like that. But you need to make it perpendicular. To make it perpendicular, you need to have it turn by theta, right? If this turns by theta, if these two have to remain perpendicular, as this turns by theta, this also has to turn by theta. Very simple point. All of them have to turn by theta. So, which means if this guy makes a turn of 360 degrees, this will also make a turn of 360 degrees. It's just starting here, that's all. It makes a turn of 360 degrees. So if that has a time period 2 pi by omega, this has a time period 2 pi by omega. Now the question is, for this point to go around, who is dragging this point along? V. Okay, so V makes you go around. So how much have you gone around? There you can say, for example, in that part, you can say that the amount you have gone around is 2 pi r. The amount you have gone around is 2 pi r. Divided by t is the speed of going around. Can you see that? 2 pi r divided by t must be the speed of going around. So this must be v. What is 2 pi by t? Omega. So clearly v must be omega times r or r omega. Is that understood? When I go around like this, I am going 2 pi r. 2 pi r is the amount you traveled around in how much time? In capital T seconds, right? Time period. So 2 pi r by t must be the speed at which you are traveling around. Now this guy, this point A, you going around and you coming back to A. How much have you traveled around? If you want to think about how much you have traveled around, you should say 2 pi v, right? 2 pi v, because this length is like v. So if I went around 2 pi v by t, what is this quantity? Here at least it's clear, you had some distance divided by time. Here I had a change in the speed or change in the velocity divided by time. In some sense, this is not exact. Okay, I want you to just understand this. This is what we should think of as acceleration. Because who changes the velocity? Acceleration. Who changes the position? Radius vector is changing means position is changing. Who is changing that? Velocity. So velocity is the reason this fellow is turning around. What is the reason velocity vector is turning around? Acceleration. Okay, it is the acceleration which is grabbing you and basically making you go around. So 2 pi v by t, what is this? Omega. So therefore this is v omega. Okay, I know this is not like proper proof because I have not told you, I just told you 2 pi v by t is equal to v omega, that is easy. But that is equal to a is not so clear. I'll explain that in a minute. But what I want you to understand is that the radius vector is turning because of the velocity. Okay, the radius vector is turning because of the velocity. The rate at which it is turning is omega. So the velocity is r omega. The velocity vector is turning because of the acceleration. The rate at which the velocity vector is turning is also omega because the time period is the same, the time it's taking to turn is the same, right? So it is turning by the same angle and so on. So that is the important idea. So because the velocity vector is also turning at the same rate omega, the acceleration vector must be v omega. I will now show this a little bit more formally. Okay, so let me show this a little bit more carefully. So let us think about this r. Okay, this is r vector, that is also r vector. Now you know that if I went in an arc like this angle is theta, then you can write that this is r theta. Right? Arc length is r theta. But instead of talking about the arc length, suppose I wanted to talk about this arrow, that would be called the displacement arrow, which I will write it as delta r vector. Magnitude of delta r vector. I know it is not equal to r theta because the arc length is r theta, but if theta was small, can you see that this is equal to this? So we can approximately say that this change in the r vector is equal to r into theta. That's very useful and important to keep in mind. So if that is true, then I can do the same with velocity. If this is v, that is v, and I have had a change in v, the arc length change in v, if this is theta, that should have been v theta. But I am interested in this part, not in that part. So this part, what is this? This is delta v, magnitude of delta v. I just only want to look at the length. I am going to say is v theta. Notice that these two are both the same. R theta is the arc length, but if you talk about small angles, then you can think of this, like imagine that you had a small angle. Whether you did this or you did this curve, they are both the same. You can't even see much of a difference, right? So therefore, what is the delta r? Delta r is r times theta. What is delta v? V times theta. What is delta r by t? It is r theta by t. What is delta v by t? R theta by t. V theta by t, because delta v is v theta, so v theta by t. But what is this thing called? What is the rate at which, this is called the rate at which you are changing position, or delta r by t is displacement by time. What should we call it? Velocity. So this is velocity, but we have taken the magnitude, so speed is r times theta by t. What is theta by t? Rate at which theta is changing. So r omega. This is the same as r omega. But what is this? Velocity change. Now this is properly defined. Not like this. When I went around like this, it was not so clear. But now, for small amount of time, I have had a change in velocity. This velocity vector becomes that. So change in velocity vector by time. So that is acceleration. Very clearly acceleration. And this is equal to v times theta by t, which is omega. So you can talk of, just like v equals r omega, we can also think of a equal to v omega. Let me explain this once more. Like you have r theta, like you can talk of r theta, right? If this is theta and this is r, you can also talk about the fact that the rate at which you are moving is r omega. So whenever somebody is moving like this, the rate at which you are moving is r omega. How much you have moved is r theta, by time is r omega, right? So this is the rate of movement. If I had a velocity vector and it was moving like this, the rate of the velocity vector's movement is v omega. But what is the rate of velocity vector's movement? Acceleration. So therefore acceleration is v omega. So let us be very clear. This velocity vector is turning around. The velocity vector's rate at which the velocity vector is turning angle is omega. It is turning by the same angle as r. So when it turns, what is the speed at which it is turning? Omega. What is making this change happen? A. So how much is A? V omega. And not just that, here you saw that what was the case? V was perpendicular to r. Right? When you make this really small, it is perpendicular to r. The same way, because you are moving in the tangential direction. In the same way, acceleration is perpendicular to the velocity. When you come here, acceleration is going to be like that, so which means it's perpendicular to the velocity. Here, acceleration is perpendicular to the velocity. At every point, A is perpendicular to the velocity. So I hope this is clear. Okay. We can do some more formulas with this. You know that V equals R omega, which means V by R is omega. So I can replace omega by V by R. So I can write A equals V omega, V into V by R, which makes it V square by R. Okay. But we can also start with omega being, right? So we can write omega, keep it as it is, and write V as R omega. And so we get R omega square. So I can write acceleration in three different ways. V omega, V square by R, R omega square. We will use all three forms. Okay. I like this form because it's nice and symmetric. A equals V omega, V equals R omega, V equals R omega. It looks exactly like this. Okay, and if you combine these two, you will get the other two. So let us keep this in mind. So this acceleration is v omega, that is the magnitude of acceleration. Just like velocity is r omega is not really velocity, it is the speed. The same way this gives us the magnitude of the acceleration. So I hope that is clear. Let me just quickly summarize some of these points. So when the particle is moving around like this, the velocity is r omega and its acceleration happens to be, if you look at the velocity change, it is also changing at the same rate as the r is changing, and so the acceleration is v omega. So I hope that part is clear. Now what is the direction of this acceleration? Direction of the velocity was clear, it is like this. And when I am saying direction of acceleration is tangential, it is tangential to what? To the velocity circle. But this is not the real circle, that is the real circle. Okay, but the acceleration is perpendicular to the velocity like this. But you have to move this acceleration here because the particle is sitting here. The particle is not sitting there. So if you move it to this place, you can say the acceleration is like that. But is this the particle or is this the particle? The particle is there, huh? No, right? It's here. So the particle is here. Where should the velocity be? Here. That's what I have drawn. Where should the acceleration be? Here. But if I put the acceleration here, the acceleration is pointing to the center. So the acceleration points towards the center. Radius vector points away from the center. Acceleration vector points towards the center. It's very important to understand. Radius vector, velocity vector, and the acceleration vector is perpendicular to the velocity. Basically, you have to move it back to where the particle is. So it is parallel to the radius vector, except it is in the opposite direction. So we call this acceleration centri basically to mean center, towards the center. Petal is where basically it likes the center. So centripetal means the acceleration is pointing towards the center from the object. That is the direction of acceleration. So we in fact call this AC, centripetal acceleration. So when an object is going around in a circle like this, its velocity is changing direction and the acceleration is pointing towards the center. How much is the acceleration? V into omega. So now let us look at this question. There is a particle that is going around in a circle with uniform speed of 6 meters per second. It is moving in a circle of radius 3 meters. And we want to find the acceleration magnitude at A. Well, what is the acceleration? Acceleration you can use v square by r. You can also use v omega. You can also use r omega square, and you should always get the same answer. Okay. Now v square by r in this case is the easiest. So I can directly write acceleration is 6 square divided by 3 because v was 6, right? So 6 into 6 by 3, and so that is 2 into 6, which is equal to 12 meters per second square. So the acceleration, we call it centripetal acceleration, so I am writing it as AC. The centripetal acceleration is 12 meters per second square. That is the magnitude of the centripetal acceleration. It is going to point towards the center. So this is the acceleration direction towards the center at A. That is the first question. What is the acceleration magnitude at B? Okay, what is the acceleration magnitude at B? This is at A. At B. Well, it's not going to change, it's going to be the same. Acceleration magnitude remains the same. Why? Because it's uniform speed. So at this point, the velocity is going to be like this, 6 meters per second. The radius is still 3 meters. So therefore, the acceleration is still 6 square by 3, 12 meters per second square. The only difference is that at this location, the acceleration points like this. At this location, the acceleration is going to point like that. The magnitude is going to be the same, the direction is going to be different. Okay, so this is hopefully clear, but let us also try to use the other formulas to calculate. So what is the omega for this question? Like, what is the omega of this object? What is the angular velocity of this object? V by r. So angular velocity is 6 by 3. So that is 2 radians per second. Now that I have found omega, I can use that to calculate A by using V omega. So if I said it was V omega, V is 6 meters per second, into omega. So 6 into 2, 12. So this is another way in which we could have calculated acceleration, centripetal acceleration. We could have also done acceleration is r omega square. Omega is 2, so 2 square. R is 3, so it's 4 into 3, 12 meters per second square. So different questions we will probably use v square by r or v omega or r omega square. They are all the same answer. And remember, omega we can calculate by using v by r. Now, if I look at the fact that this is r and the v is changing my r, I can write omega as v by r. Omega is v by r. V is basically making r turn around at the rate omega. But we can also think of this v turning around because of the acceleration. This acceleration is making v turn around. At what rate? The same rate. So we can see that this v is also turning around, right? Who is making v turn around? A is making v turn around. So A by v is the rate at which this turning around happens, and that is omega. So we will use this idea again and again. So basically v by r is omega, A by v is omega. So we will use this to understand the idea of centripetal acceleration a little bit more. Let us now try to understand this a bit more carefully. So here I have the radius vector and I have the velocity vector, right? Velocity vector is perpendicular to the radius vector. As the velocity vector pulls the radius vector along, it is also turning, right? So as it moves around, the velocity vector turns by the same amount as the radius vector. That's what we saw. What does that mean? That means the angular change of the velocity vector is the same as the angular change of the radius vector. So both have the same angular velocity, both have the same time period, right? So both are turning at the same rate. Velocity is basically making the radius vector turn, right? This turn is because of the velocity vector. And who is trying to make the velocity vector turn? Why is the velocity vector turning? Because of the acceleration. So this is the acceleration vector. See, this velocity vector is making this turn. This guy is pushing or pulling this point and it's going that way. Who is making this point turn around? Because this also is turning around, right? When it comes to this place, the velocity vector has to look like that. So why is the velocity vector turning around? Because of the acceleration. And so the velocity vector is turning because the acceleration is pulling it this way. And how much is that? V omega. Okay, the rate at which the radius vector turns, that is equal to the rate at which acceleration vector turns. So whenever something is turning, this is the rate at which it is turning. Okay, this is the omega. It is not theta, I'm talking about omega. This is r. So if I call this v, then v by r is omega. Correct? V by r is omega. So just like saying, this could have been written as Vt. Vt by r, what is Vt? It should be S. S by r is theta. Correct? Vt by r should be theta. Vt by r should be equal to omega t. Instead of writing the t, I am just writing, right? So, well, I should then divide by t here also. Okay. So, if I cancel out the two t's, then you can see that V by r is equal to omega. So what does that mean? Whatever is turning, whatever is making you turn, that thing divided by r is the rate at which you are going to turn. The rate at which you are turning is omega. The same thing, if I had the velocity vector, who is making the velocity vector turn? Acceleration. And so this is still omega. So A by V must be omega. So A by V is omega means A equals V omega, right? And V equals R omega. But if I write this, you can see A must be equal to V square by R, because you can just take the V there. I can also do this by saying AT is the reason V has turned in some time t, but that means it would have covered an angle omega t, and then you can write AT by V is omega t, is the angle. correct? And if I cancel out the t, you will get a by v equals omega. So very simple. V turns r at the rate of v by r. A turns v at the rate of a by v. The rates are the same. So v by r is the rate at which v is turning r. A by v is the rate at which a is turning v, and both are exactly the same rate, omega. So I hope this idea is clear. That is the essence of centripetal acceleration, whole of uniform circular motion. This is the most critical idea. Okay, the rest of it is all like formulas and stuff that we will put in. But I want you to first understand this. Second thing I want you to understand is that this acceleration is perpendicular to the velocity. Just like velocity was perpendicular to the radius, acceleration is perpendicular to the velocity. But you can't talk about the acceleration basically pointing this way because there is nothing there. The particle is sitting here. So move this acceleration here. So the acceleration is actually pointing to the center. So we call this the centripetal acceleration. I want you to keep in mind that the centripetal acceleration points like this here. When you are here, it points like this. It's always pointing towards the center. When you are here, the centripetal acceleration is this. When you are here, it is this. When you are here, it is this. It's always pointing towards the center. So is it constant acceleration? No. The magnitude of the centripetal acceleration is constant. V omega, V square by R, right? R omega square. All of these are constant. So this is constant in magnitude. It is not constant in direction. It is always pointing radially towards the center like this. If you are here, it points like that. Okay? It is always in the opposite direction. So it varies in direction. Varies in direction. Always towards the center. Okay? The second important thing is I can write this in a vector kind of form. So suppose I was talking about this being my r vector. The direction from like this along away from the center would have been called r cap. Always r vector is pointing from the center to the particle. So it is like this, it is like this. This is called the radius vector, right? It is pointing away. But the acceleration is pointing this way. How much is the acceleration? Acceleration, centripetal acceleration is r omega square in this direction. But if this direction, unit vector in this direction, we called it r cap. The unit vector in that direction, we should call it minus r cap. So what direction? Minus r cap. If I wanted to put it with an arrow, I should write it like this. But what is r times r cap? R times r cap is r vector. So you can just combine these two and write it as minus omega square r vector. Notice the minus. Okay, that's why this centripetal acceleration is opposite. It highlights the fact that it is opposite to the r vector. We won't use it in so many ways, but I want you to understand that the centripetal acceleration is always pointing opposite to the radius vector. Acceleration and radius vector, they are in opposite direction. This is a positive number. Okay, so the minus sign clearly tells you that it is in the opposite direction. Also remember that at this location, the acceleration vector is very different from at this location. The magnitudes are the same. As vectors go, acceleration is varying. It is not uniform acceleration. It is not. Okay? When you are going in uniform circular motion, the acceleration is not constant. What is constant is the acceleration magnitude. Only the magnitude is constant, not the acceleration. I hope that is clear. The acceleration changes in direction. So you cannot use any of the uniform acceleration motion formulas because it's not uniform acceleration. Only thing is that the magnitude is constant and it is always pointing towards the center. Okay, so I hope this is clear. The best way to understand this is to apply these formulas and look at how we can use the idea of centripetal acceleration in doing different kinds of questions. So let us look at a few examples. So in this question, there is a particle that is going around with a uniform angular velocity of 2 radians per second. It is going around in a circle of radius 5 meters. And we want to find the radius vector remember it's a vector, velocity vector and acceleration vector when the angular position is 0 degrees, 90 degrees and 37 degrees. Okay, this is the I cap and j cap vectors, and of course you know that sine 37, cos 37, the values are 3 by 5 and 4 by 5. Let us think about it. When the particle is here, the angle is 0, so at 0 degrees, the vector is pointing like this, right? So what will be the r vector? R vector will be 5 in the I cap direction, so 5 I cap meters. What would be the velocity vector? The velocity vector is going to point like this, right? V. How much is V in magnitude? It is r omega. R is 5, omega is 2. So it is 10 meters per second. So this is 10 meters per second. But it is not pointing like this, it's pointing like that. It is perpendicular to r and it is going to be, look at the omega. Omega is like this. So velocity vector could be perpendicular like that or like this, but in this case it is upwards. And so I should be saying 10 j cap. So the velocity vector is 10 j cap meters per second. Notice that this was 5 I cap, this is 10 j cap. What about the acceleration vector? Acceleration, we can say is r omega square, or we could have said v square by r or v omega, whichever way. R is 5, omega is 2, so r into 2 square, 5 into 2 square, 4 into 5, 20 meters per second square. This is the acceleration. If I had done the same by using v square by r, I would have got the same thing, 100, v square is 100 because 10 square by 5, that also gives me 20. Okay, the acceleration magnitude is not the problem, that is 20. What is the direction? It's going to be like this. So this is 20 meters per second square in this direction. If that is I cap, this is minus I cap, right? So this is minus 20 I cap meters per second square. I want to also calculate what would be omega square r vector. Omega square times r. Omega square is 4, right? 2 square. So 4 times r will give me 20 I cap. Can you see that this is minus? So minus omega square r is minus 20 I cap. So this and this are in opposite direction, I cap and minus I cap, except that this is also omega square times r vector with a minus sign. So minus omega square r. So this is the acceleration vector AC is minus omega square r. We'll see that in all the other cases as well. Now let us go to theta being 90 degrees. Well, theta is 90 degrees. The r vector is pointing like that. That is 5 j cap. So r is 5 j cap meters. And what about the velocity vector? The velocity vector is now going to be in this direction. It has the same magnitude, 10 meters per second. And it is going to be in the minus I direction. So this is minus 10 I cap meters per second. Remember that it is minus 10 I cap, not 10 I cap, minus 10 I cap. You could have had 10 I cap, but if you had that, then that means it's going in the clockwise direction, whereas this thing is clearly saying that it's anti-clockwise. What about the acceleration? The acceleration again is going to have the same magnitude 20, but it's going to point towards the center. So acceleration vector is going to be minus 20 j cap. This is plus j cap, this is minus j cap, notice that again. Okay, and again 5 into 4 is 20. So this is also clear, minus 20 j cap. Right? These two are not equal. I'm just saying that this quantity is equal to that. Let me draw it like a line like that. Let us now look at what happens when the angle is 37 degrees. What is 37 degrees? This is 37 degrees. The velocity vector is going to point like that. The radius vector is going to be like this, the velocity vector is going to be like that, the acceleration vector is going to point in the opposite direction to the radius vector. But if this is 37, this is r5. So the x component, let me draw it separately. If this is 37 degrees, this is 5. the x component is 5 cos 37. Now cos 37 is 4 by 5. So 5 times 4 by 5 is 4. And then this is 5 sin 37. So that is 3 by 5 into 5 is basically 3. So you have 4i cap plus 3j cap. So 4i cap plus 3j cap meters. So you are moving 4i cap and then you are moving 3j cap. So the r vector is 4i cap plus 3j cap. But what about the velocity vector? The velocity magnitude is 10. But let us think about the direction and angle and so on. So you can see that you must have turned. This has turned by 37. This must have also turned by 37. So this angle must be 37. Let me show it to you much more using a little bit more geometry. If I drew two parallel lines, this is 37, this is 37. So this angle, because this is 90, this is 37, that angle must be 90 minus 37, 53 degrees. And so if I move to this side, that is again 90. So this must be 37 degrees. So this angle is 37 degrees. But we should already know it, because if r turns by 37, you know that the velocity must also turn by the same angle 37. Okay. So but if this is 37, that means 10 cos 37 is the vertical direction. So let me show that here. This is the vertical, this is 37, 10. So 10 cos 37, 10 into cos 37 is 4 by 5. Okay, so that is 8. And then this direction should be, this or this should be 10 sin 37, which is 6. So the components of the velocity vector is 8 upwards and 6 to the left. So I should write minus 6i cap because it's to the left, plus 8j cap meters per second. So this is how you will write the velocity vector. What about the acceleration vector? The acceleration vector points in this direction. Magnitude is still 20. Okay, so it is going to be opposite direction to the r vector. So how will I calculate that? So the acceleration vector is going to be like this, and so if I draw it, okay, this is 20. This angle is 37. So this is 20 cos 37, but it's going to point like this. So 20 into 4 by 5. How much is that? 16, right? But it's in this direction. And then this is 20 sin 37. So that is 3 by 5. So that is going to be 12. So it is 12 down and 16 to the left. So the acceleration must be minus 16 I cap minus 12 j cap meters per second square. I did not use the fact that it was opposite to the radius vector. I just directly wrote this down, right? So minus 16 I cap minus 12 j cap. But if I had used this calculation, this is where it is useful, otherwise it's not so useful, right? Is minus omega square, omega is 2, so minus 4 times the radius vector, 4i plus 3j. If I did this, I am going to get minus 16 I cap minus 12 j cap meters per second square, and so that you can see matches with what we have got. There we took the magnitude 20 and then we resolved it and found the answer. Here we are just writing it as minus omega square times the r vector. R vector I already know. So minus, remember the minus basically brings the direction in the opposite direction. We could have also done directly by saying, hey, I know that the unit vector in this direction, unit vector in the r direction is r vector by the magnitude of r, which is 4i plus 3j by 5, because the magnitude of r is 5. If I know this, then you can say this is the direction vector, and we need to basically have the magnitude multiplying by the direction vector. So therefore acceleration vector is 20 times 4i cap plus 3j cap by 5. But this is the direction vector like this. We want it in this direction, so put a minus sign. So we'll put a minus sign. So if I did that, this is 4. So therefore you can cancel it out and get minus 16 I cap minus 12 j cap meters per second square. So many different ways of calculating that. What I want you to keep in mind is that the acceleration vector when the particle is here is like this, there it is like that, and here it is like this. As a vector, the vector is very different. Okay, so at various locations the acceleration vector is very different. Here the answer is different, here the answer is different, there the answer is different. You can see that as the position changes, the acceleration vectors, they are all very different. The magnitude of the acceleration vector, of course, everywhere is just simply 20, 20, and if I took root of 16 square plus 12 square, this would also give me 20. So the magnitude is the same, but look at the vector directions, they are very, very different. So just something that you should keep in mind. It is not a case of uniform acceleration. It is a case of uniform magnitude, but the direction keeps changing. So the acceleration is not uniform. It is constantly changing in direction.